we would like to know how to integrate the Gaussian integral, I'll call it I, and that is equal to the improper integral from minus infinity to infinity of e to the negative x squared dx. Okay, so let's just take a look at what the graph looks like. So here's my x-axis, here's my y-axis, and the graph of e to the negative x squared looks something like this. Okay, not that well drawn, but essentially you have this bell-shaped curve, and we're curious as to what the area underneath that graph is equal to. So if I is equal to this, I can rewrite this same expression but change the variable x to the variable y. So we have the improper integral from minus infinity to infinity e to the negative y squared dy. And this is fascinating because this implies that if I square y, that's the same thing as I times I. By I can rewrite one of those i's as negative infinity to infinity improper integral e to the negative x squared dx, and the other I as the improper integral from minus infinity to infinity e to the negative y squared dy. And this gets us into the three-dimensional realm. Okay, so we apply some multivariable calculus over here, and what we get is that, okay, this, the product of these two, is actually equal to the double integral of, and then you just multiply the integrands together, e to the negative x squared times e to the negative y squared. And if we do, let's say, dx dy, we just need to make sure that the inner integral limits of integration matches with x, and the outer limits of integration matches with y. But since both x and y, their limits of integration are from minus infinity to infinity, it does not matter in this case. So we have minus infinity to infinity here. Okay, that's pretty good. So now let's just use some exponent laws and simplify this by combining them. So we have the double integral from minus infinity to infinity, minus infinity to infinity, e to the negative x squared minus y squared, and then dx dy. Okay, we can totally do dy dx in this case as well. Okay, you're going to get the same thing. Now, we can actually factor out a negative sign from this part. So we have e to the minus x squared plus y squared dx dy. Now, for those of you who know multivariable calculus, we can use polar coordinates, okay, as a change of variables. So we can let r to equal to x squared plus y squared, okay? And then, oh, sorry, there should be r squared. R squared is equal to x squared plus y squared. Then we get that dx dy is equal to r dr d theta, okay? I won't derive why this is the case in this video, but take it as it is. So we do a change of variables. Essentially, a change of variables is the u-substitution for higher dimensions, okay? So then instead of e to the negative x squared plus y squared, we will have e to the negative r squared, and then dx dy becomes r dr d theta. Now, because we made a change of variables, we also need to change the limits of integration. What this is essentially saying, if x is going from minus infinity to infinity and y is going from minus infinity to infinity, we are integrating over the entire xy plane, the entire Cartesian plane. R here represents the radius in polar coordinates, and then theta is the angle. Equivalently, if x goes from minus infinity to infinity, y goes from minus infinity to infinity, we can also say that r, the radius, starts at the origin, so it will have a radius of 0, And like a ray, it shoots out like a laser beam to infinity. So radius will go from 0 to infinity. But if you take that ray and you rotate it 360 degrees, you pretty much, yes, you capture the entire xy plane. So that is why we have theta going from 0, and because we're working with radians, theta goes from 0, not to 360 degrees, but we say 2 pi radians. Okay? Then this is just what? This is a baby integral. We can integrate this pretty well. We can do some u-substitution over here. So we can say that, okay, if we know that the derivative of e to the negative r squared is e to the negative r squared times negative 2, well, we can have a negative 2 right there. Okay, we have that negative 2r, right? Negative 2r is the derivative of negative r squared. But we cannot just multiply this negative 2 randomly. I'll need to multiply a negative 1/2. Let's say take it out because it's a scalar. And these two will cancel to become 1. Okay, and this is going to equal to the double integral from 0 to 2 pi, 0, actually this is already integrated, so we can say this is equal to e to the negative r squared, okay, but with that negative 1/2, okay, and because in this integrand we don't have any thetas, you can essentially break this up, okay, we can break this double integral up, okay, so let me just rewrite this as negative 1/2, okay, actually right over here, negative 1/2, I guess the camera quality, okay, it doesn't capture your range, so negative 1/2, integral from 0 to 2 pi of just the theta, and then integral from 0 to infinity of, well, if I just integrate this part, well, I know what it is. It's just e to the negative r squared, and I'm integrating from 0 to infinity, okay? And then here, the integral of 0 to 2 pi of just d theta, that is just equal to 2 pi, okay? So we have 2 pi. We take this and put infinity into here, or take the limit as r approaches infinity over here, we're going to get 0, okay? And then when we plug 0 into here, we're going to get 1. So we have 0 minus 1, which is equal to negative 1. But negative times negative gives you a positive, and these 2's will cancel out. So altogether, you actually get pi. So this integral evaluates to pi. However, we need to understand that we need to find out what I is, okay? But this pi is the answer to I squared. So this implies that I is equal to the square root of pi. Now, you might be wondering, is it the plus or the minus, okay? Because we could have negative a square root of pi, and then you square it, and that also gives you pi, okay? Make sure we understand that the square root only gives you one answer. It gives you the non-negative value. If you look at the original graph right here, we see that the area is above the x-axis, which means we want to take the positive square root of pi. And that's it. The Gaussian integral evaluates to the square root of pi.